Hi everyone, I'm Yinzhan. Today I'm going to talk about Fredman's trick means dominance product, fine-grained complexity of unweighted APSP, three-sum counting, and more. This is joint work with Timothy M. Chan and Virginia Vassilevska Williams. Let me first introduce the two concepts mentioned on the title. First, Fredman's trick. It was introduced for solving OPS shortlist passes, or APSP, faster. APSP is known to be equivalent to the following mean plus product problem, in which we are given two n-bound matrices A and B, and we need to compute an n-bound matrix C, where Cij is the minimum value of Aik plus Bkj over all possible k. If k is a minimizer for the above minimization, then Aik plus Bkj is less than or equal to ARL plus BLJ for every L. By rearranging it, we get that Aik minus ARL is less than or equal to BLJ minus Bkj. This is the Fredman's trick. Even though it seems simple, the idea of making the left-hand side purely in terms of A and the right-hand side purely in terms of B can lead to powerful consequences. Practically, all subcubic algorithms for APSP use Fredman's trick. In the dominance product problem, we are given two n-by-n matrices A and B, and we need to compute an n-by-n matrix C, where Cij is the number of k such that Aik is less than or equal to Bkj. It's known to be equivalent to the following equality product, where here, for each Cij, we have to count the number of k such that Aik is equal to Bkj. It's known that dominance product can be computed in roughly n to the 3 plus omega over 2 time, where omega is a matrix multiplication exponent. The best officially published upper bound for omega is 2.373, and our archive there is a preprint by Duan, Wu, and Zhou that claims an upper bound of 2.372. If we use rectangular matrix multiplication, then the upper bound for dominance product can be slightly improved. The main theme of our paper is that we combine these two techniques to obtain new results. For instance, we show the equivalence of counting and detection versions of many problems. We also show conditional lower bounds for problems with intermediate complexity or intermediate problems. Intermediate problems refer to problems whose running times become roughly n to 2.5 when omega is 2. So the previously mentioned dominance product and equality product are both examples of intermediate problems. We also show new variants of the Borlaug-Semeradi-Galois theorem, and we provide algorithmic application. These are the three main sets of results of our paper, but we also have some other results not listed here. In this talk, I will focus on the first two, equivalence of counting and detection and conditional lower bound for problems with intermediate complexity. First, counting and detection. For many core fine-grained problems, the best running times for counting the number of solutions and detecting whether there is a solution are essentially the same. For instance, in the three-sum problem, we are given n integers and we need to decide if there are three integers that sum to 0. In its counting version, which we call counting three-sum, we instead have to count the number of triples that sum to 0. For both of them, the current best running times are essentially n squared. The mean plus product problem we mentioned earlier also has a natural counting variant. Here, we are given two n-by-n matrices A and B, and we need to compute an n-by-n matrix D, where Dij equals the number of k prime, such that Aik prime plus Bk prime j achieves the minimum. For both mean plus product and counting mean plus product, the current best running times are essentially n cubed. So, a natural question is whether the counting version and detecting versions of these problems are equivalent. There are some partial progress towards this open problem in prior works. It was known that the detection version of many problems are equivalent to the approximate counting versions. And also, the detection versions of many problems are equivalent to the counting versions if the counts are small. However, in general, it was not known whether the detection versions are equivalent to the exact counting versions. We proved the equivalence between the counting versions and detecting versions of many problems. For instance, we show that three-sum convolution, and mean plus convolution are subquadratically equivalent to their counting versions. meaning that if the detection versions of these problems has a truly subquadratic time algorithm, then so do the counting versions, and vice versa. We also showed that exact triangle and mean plus product are subcubically equivalent to their counting versions. We also proved such equivalence for a few other problems. For exact k-clique and minimal k-clique, we show that they are sub n to the k time equivalent to their counting versions. For monochromatic convolution, we show that it is sub n to the 1.5 time equivalent to its counting version. For APSP, we're not able to show that it is equivalent to its counting version, mainly because that the number of shortest passes between two given vertices in a graph can be exponentially large. In the worst case, we have to use essentially n bits to represent such a count. And therefore, the trivial algorithm for counting APSP is actually n to the fourth. However, if we only need the counts more some given number u, then we can still show that APSP is equivalent to this variant of counting APSP. In the following, I will prove that exact triangle is equivalent to its counting version. So in the exact triangle problem, we are given an n-balanced matrix A representing the edge weights of a graph. And we need to decide if there are three vertices such that the edge weights of the triangle of these three vertices sum up to 0. In the counting exact triangle problem, we have to count the number of such triangles. The exact triangle hypothesis is a popular hypothesis in fine-grained complexity, and it says that exact triangle essentially requires n-cube time. It's known that the exact triangle hypothesis holds as long as one of the APSP hypothesis and the three-sum hypothesis holds. So people have been using it to show very believable conditional lower bound, because if a hardness result holds on the exact triangle hypothesis, then it will also hold on the either the APSP hypothesis or the three-sum hypothesis. And we will show that exact triangle and counting exact triangle are subcubically equivalent. First, it's trivial to reduce exact triangle to counting exact triangle, because once we know the count, we will know that whether there is at least one exact triangle. And it remains to prove the other direction. Here's the setup of the proof. We'll assume that exact triangle has a truly subcubic time algorithm, and then we need to show counting exact triangle has a truly subcubic time algorithm. The following is known. If exact triangle is in truly subcubic time, then for every edge ij, we can list up to n to 0.99 many k, and we call such k witnesses, where ijk forms the exact triangle. And we can do this in truly subcubic time. This means that if an edge ij is in less than n to 0.99 exact triangles, then we are able to list all of them. Therefore, it remains to consider ij that are in at least n to 0.99 exact triangles. And we call that the many witness case. For this case, we do the following. First, we sample a random index L. Then we create matrices X and Y, where Xik equals Aik minus Ail, and Yjk equals Ajl minus Ajk. Then we use equality product to count for every ij the number of k where Xik equals Yjk. The running time of each iteration of this is roughly n to the 3 plus omega over 2, and it's essentially the runtime of the equality product. So now let's see why it's useful. If L forms an exact triangle with an edge ij, then what can we say about what k forms an exact triangle with ij? So first, by observing that ajk plus aik and ajl plus ail both equal to negative aij, we see that both of them are equal. And then by rearranging the equality, we get that aik minus ail equals ajl minus ajk. And this step is exactly Fredman's trick. And finally, by definition of x and y, we get that xik equals yjk. And we already have the count for the number of such k. Therefore, by reading the result of the equality product, we will be able to get the number of k such that ijk is in an exact triangle. And this means that if we have some L that forms an exact triangle with ij, then we will be able to compute the number of exact triangles ij is in. Because we are considering the many weightiness case, we can assume ij is in at least into 0.99 exact triangles. So we only need to sample into 0.01 many L in order to hit one weightiness with high probability. Therefore, the running time is truly subcubic. The proof for the equivalence of other problems share the same underlying idea, but some reductions are more complicated. For instance, for the equivalence between three-sum and counting three-sum, we combine this idea with the known reduction from three-sum to convolution three-sum, and then further from convolution three-sum to exact triangle. Okay. So now let me talk about intermediate problems. I will mainly focus on two intermediate problems. The first one is unweighted APSP. It's known that APSP in unweighted undirected graphs can be solved in roughly n to omega time. And APSP in unweighted directed graphs can be solved in n to the 2.53 time, which becomes n to the 2.5 if omega is 2. So a natural question is there a reason why unweighted directed APSP requires more time than unweighted undirected APSP? The second problem we'll consider is mean weightiness product. It is a variant of the Boolean matrix multiplication problem in which we are given two n by n Boolean matrices A and B, and we need to compute an n by n Boolean matrix C, where Cij is true if and only if there exists some k where both Aik and Bkj are true. In the mean weightiness product problem, we instead have to find the minimal k such that Aik and Bkj are both true. And the current running time for mean weightiness product is exactly the same as that of directed unweighted APSP. So a natural question is, why does mean weightiness product require more time than Boolean matrix multiplication? And also, because the running times of mean weightiness product and unweighted directed APSP are the same, it's natural to ask whether there is a relationship or reduction between these two problems. To answer these open problems, we devise the following strong APSP hypothesis. It says that mean plus product between two n by n matrices with entries that are positive integers bounded by n to the 3 minus omega requires essentially n cubed time. And we have the following motivations for this hypothesis. First, in a mean plus product instance, if the entries are small integers, then there's a faster algorithm than n cubed. So if the entries are positive integers bounded by m, then we can compute the mean plus product in roughly m times n to the omega time. So if we plug in m equals n to the 3 minus omega, we get an essentially n cubed time algorithm. And there has been no improvement over this algorithm. Also, there exists similar variant for the three-sum hypothesis, which is called the strong three-sum hypothesis. And it also considers three-sum where the input numbers are small integers. And here are our results. We show that under the strong APSP hypothesis, unweighted directed APSP requires essentially n to the 7/3 time, and the mean weightiness product requires essentially n to the 11/5 time. This theorem provides some reason why unweighted directed APSP seems harder than unweighted undirected APSP, and why mean weightiness product seems harder than Boolean matrix multiplication. We also provide a reduction from unweighted directed APSP to mean weightiness product. More specifically, we show that if unweighted directed APSP requires essentially n to the 2.5 time, then mean weightiness product requires essentially n to the 7/3 time if omega is 2. And it is worth noting that in the first theorem, the time bounds hold regardless of the value of omega. We also showed conditional lower bounds for several other problems on these two hypotheses in our paper. In the following, I will prove the conditional lower bound for unweighted directed APSP under the strong APSP hypothesis. And here's the setup. We will assume unweighted directed APSP can be solved in faster than n to the 7/3 time. And we'll also assume omega is 2. It is not necessary, but assuming it will simplify the proof. And the goal is to show that mean path product between two n-binomial matrices with entries in n can be solved in truly subcubic time. So the first step in the reduction is to create several matrices. We set A prime ik to be aik divided by n to the 1/3 round down, and A double prime ik to be aik mod n to the 1/3. And we similarly create B prime and B double prime. By some reasoning, we can assume without loss of generality that A double prime ik and B double prime kj are all less than n to the 1/3 over 2. So now, using these newly created matrices, we can rephrase our goal as the following. So now, for every ij, we need to find k that primarily minimizes A prime ik plus B prime kj. And if there are ties, we have to secondarily minimize A double prime ik plus B double prime kj. And we have to do this in truly subcubic time. So here's the proof outcome. We'll first compute the mean path product C prime between A prime and B prime, because the entries of A prime and B prime are bounded by n to the 2/3. We can do this in n to the 2/3 times n to omega time, and we are assuming omega is 2, so the runtime is essentially n to the 8/3. And now we call some k a weightiness for ij if C prime ij equals A prime ik plus B prime kj. And we also consider two cases, the few witness case and many witness case. If ij only has a few witnesses, then we'll find all the witnesses. And if ij is in many witnesses, we'll use a variant of equality product to solve it efficiently. Let's first talk about the few witness case. We call the number of witnesses few if the number of witnesses for ij is at most n to the 2/3 plus epsilon over 2. And then we repeat the following for roughly n to the 2/3 plus epsilon over 2 times. First, we randomly keep a subset k of indices of size roughly n to the 1/3 minus epsilon over 2. And then we compute the mean plus product between two submatrices of A prime and B prime. For A prime, we keep all the columns whose indices are in the subset k, and for B prime, we keep all the keep all the rows whose indices are in the subset k. And then we compute the mean plus product between these two submatrices. And also, for every ij, we will find the witness for this mean plus product. It's not hard to see that each witness for ij is found as a witness in some inner loop with high probability. And also, the cost of finding a witness for each ij is nearly the same as the cost of the computing the mean plus product itself. So we'll ignore the cost of it in the following. And the dimension of A prime star k is n by n to the 1/3 minus epsilon over 2, and the dimension of B prime k star is n to the 1/3 minus epsilon over 2 by n. Also, the entries of these two matrices are integers bounded by n to the 2/3. Now we aim to solve this fast. Recall that we can assume that unweighted directed APSP can be solved in n to the 7/3 minus epsilon time. And it was known that mean plus product between an n by x matrix and an x by n matrix with entries in n over x can be solved in the same time as unweighted directed APSP. And if we use x to be n to the 1/3, we get that mean plus product between an n by n to the 1/3 matrix and an n to the 1/3 by n matrix with entries in n to the 2/3 can be solved in n to the 7/3 minus epsilon time. And observe that the dimension bounds and entry bounds for this mean plus product are all upper bounds of the dimension and entry bounds of the mean plus product we want to compute. Therefore, for each iteration, we can compute it in n to the 7/3 minus epsilon time. And there are n to the 2/3 plus epsilon over 2 iterations in total. So overall, the running time is roughly into the 3 minus epsilon over 2. That concludes the field witness case. Now we focus on the many witness case, in which we want to consider Ij, whose number of witnesses is more than into 2/3 plus epsilon over 2. For this case, we will repeat the following iteration multiple times. In each iteration, we first sample a random index L, and then we create matrices X and Y, where Xik is defined as A prime Ik minus A prime Il, and Ykj is defined as B prime Jl minus B prime Jk. Now, suppose L is a witness for Ij, which means that A prime Il plus B prime Lj has a minimal value over all possible L. Then recall that our goal is to first primarily minimize A prime Ik plus B prime Kj, and then secondarily minimize A double prime Ik plus B double prime Kj. So the left-hand side here is the quantity we want to minimize for Ij. And by definition of Xik and Ykj, we can equivalently write it as the right-hand side. And this is exactly the Fredman's trick. So now the goal becomes that for every Ij, we want to compute the quantity on the right-hand side. And recall that A double prime and B double prime have entries bounded by into the 1/3. We call this problem generalize the equality product, and when the entries of the two matrices are integers bounded by into 1/3, we have an algorithm that can compute it in roughly into 8/3 time if omega is 2. And we will omit the proof of this lemma in this talk. So now each iteration will take roughly into 8/3 time. And in order to hit a witness for every pair of Ij that has at least into the 2/3 plus epsilon over 2 witnesses, we have to repeat roughly into the 1/3 minus epsilon over 2 times to hit one witness with high probability. So the overall running time becomes into the 3 minus epsilon over 2. So recall this is the outline of the proof. And for both the field witness case and the many witness case, we can solve it into the 3 minus epsilon over 2 time roughly. So overall, we get a truly subcubic time algorithm for our goal, and that concludes the proof. Finally, I want to list other results in our paper. I won't talk about each one of them, but I want to briefly mention the truly subquartic time algorithm for counting APSP. We mentioned that the trivial algorithm for counting APSP runs in roughly into the 4th time. And in our paper, we give an algorithm that runs in roughly into the 3.75 time if omega is 2. That's all. Thank you.